Okay, so last time we were talking about the time complexity, and the last thing which we discussed was the difference between the performance and the complexity of an algorithm, right? So performance is actually the amount of time or space, rather amount of time and space which an algorithm consumes while executing, whereas complexity refers to the scalability of the algorithm in terms of its requirements in terms of time and space as the size of the input grows. So this complexity refers to the scalability of an algorithm. For example, if you see this graph, this blue line is more scalable than this red line, right? Because as the size of the input increases, the requirement of red line in terms of maybe number of steps is increasing exponentially, whereas the requirements of this blue line is increasing linearly. So it means that this blue line whatsoever algorithm it is representing, it is more scalable, right? So complexity refers to the scalability of an algorithm. Now if you recall, I told you that I have not yet discussed this asymptotic complexity, right? So in this particular lecture we will be discussing the asymptotic complexity term. Otherwise, if in the literature and other tutorials, if you see such equations which are extracted from the, or rather computed from the piece of code or pseudocode or algorithms, they refer to as the complexity function or asymptotic complexity itself. After dropping this insignificant and inaccurate terms, now we are remained with this. So this is usually referred to as asymptotic complexity, but actually it is sort of the same, but the theoretical concept must be followed. So I'm going to explain that. Now the f of the 5n plus 3 time bound is said to grow asymptotically like n, right? If you see here, when we compute this complexity function, so and when we compute this complexity function and we draw the graph of it, and we saw that this is linear, right? So this shows the bound, this shows this line, this green line shows the bound of this particular piece of code. Bound on what? Bound or limitation, and bound or limitation on what? That is the number of steps, right? And again, for example, we are not here talking about the exact time, because when we say that an algorithm consumes 10 steps to execute, and we say okay, two steps require 1 unit of time, 1 unit of time, 1 unit of time. So it means that this 1 unit of time does not refer to 1 second or 1 millisecond or 1 minute for that matter, because this 1 unit of time can vary from processor to processor, from operating system to operating system. For example, 1 unit of time may be 1 second on a Pentium 4, but 1 unit of time may be half a second on let's say a Core i7 machine, right? So coming back to what I was saying, that this linear line, this green line, shows the bound that the number of steps rather the time in terms of unit of time, not in terms of minutes or seconds or hours, this algorithm will be less than or equal to this green line, right? So it may consume like this amount of time. This point may refer to some, let's say 1, 2, 3, 4, 5. So these are units of time, and for let's say input size of 1, 2, 3, 4, 5, 6, 7, so on and so forth. So for example, for an input size of 6, this algorithm may consume this amount of time. If you see here, this is like 3.2 or 3.3, but this algorithm, performance of this algorithm is bounded in this particular region, which is dictated by this particular green line. So it rest assured that the performance of this algorithm will not exceed this green line, right? So so this complexity function represents the bound on this particular algorithm. So coming back to what I was saying here, that now this 5n plus 3 time bound is set to grow asymptotically like n. Now before going to the details of this growth function, let me explain to you asymptote, right? Now for example, to give you a different example, for example, you are a student in a class, okay, and you are a student and you are a hardworking student, right? You have got few hairs on your head, you, okay, and there is another student in the class who is sort of like this, okay, and this student is a hardworking student, right? So and usually in these days, for example, if somebody is a topper of a class or good at particular course or some particular, let's say if somebody is good at programming, the slang which is used is that he or she is a theta, right? So let's assume that this student is a let's say topper of the class, right? Now I'm shifting my discussion from the world of algorithms to a different world to make you understand the concept of asymptote, right? Now if we draw a graph, for example, we have got quiz 1, we have got quiz 2, we have got quiz 3, and we have got quiz 4. And this axis, y-axis represents the score. For example, the minimum you can get 0 unless until you don't do cheating. Then let's say 2, then 4, then 6, then 8, and then let's say 10, right? And okay, let me now in the quiz 1 you score at this point, right? Okay, and this topper scores this much marks, right? This is the score of the topper, right? Then you say, okay, fine, I've got two marks and the topper of my class has got 8 marks. Now I will work hard and I will try to beat this particular student. And there is another quiz and you attempt that quiz and you end up scoring 4 marks, right? And this topper student ends up scoring, let's say, 5 marks, right? So okay, you say, okay, I've increased my score and the topper has somehow got lesser marks, and you make up a strategy that okay, I worked hard and I cannot do well, and you come up with another strategy that okay, what I will do is that I will work even harder, and then another course, another quiz comes up, and in that particular quiz you end up having let's say 8 score, right? Now this, for this particular course your score will be 8, but when the result comes, your the topper of the class has scored 10 marks. Again this topper is higher than you, and then in the fourth quiz you work really hard and you score, let's say 10, right? And when the result comes and you see your score is 10, but the topper of the class also scores 10, right? Now let me draw a line for these quizzes. If you see here, this is your trend, and let's see the trend of this topper student. You can call this student theta or whatever you like. Now if you see this topper student is your asymptote, right? Now asymptote is a point which is your upper bound. You will always remain less than your asymptote, and if you maximum exceed your limit, you can only touch your asymptote. You cannot cross your asymptote, right? So if you see here, this blue line which represents you is always less than this red line, which and the red line represents the asymptote. But if you have worked very hard, what you did, you end up reaching your asymptote, but you could not cross this asymptote, right? So this is how this is a simple example where you can better understand the asymptote, right? Now coming to the actual example, this 5n plus 3 bound is said to grow asymptotically like n. For example, if I draw the line n, for n I draw this line, and for 5n plus 3 let me draw a line, let's say green line. Okay, so its behavior after a particular point, after this particular point, it grows like the line of n. So this represents n and this represents 5n plus 3, right? So this 5n plus 3 is said to grow asymptotically like n, so it will be just like n, right? Now this gives us an approximation of the complexity of an algorithm, and while we compute that, we ignore a lot of machine level details. For example, how many cycles, for example, addition performs and multiplication performs sort of double cycles, then the addition, and what will be the operating system, and what will be the processor type, and what will be the architecture of the processor. We ignore a lot of machine level details, machine dependent rather details, and we concentrate on the bigger picture, right? So this is how this asymptotic analysis is done. This time complexity computation is also called asymptotic analysis. This asymptotic analysis or complexity analysis is a better word than the time complexity, although this series of lectures has the title time complexity. Now before explaining this point, for example, if we have a student, or rather an applicant, he wants to join military, right? So we need to have certain vitals of this gentleman to join military from the medical perspective. For example, we want to know his height or her height, for example, right, and weight. For example, the height is, let's say, 5 feet and 5.9, and the weight is, let's say, 62. Now if you see this, can you identify anything which is incomplete? can you identify any specific thing which is incomplete? Maybe not, but it is incomplete. The thing which is incomplete is the unit. Now 5.9 what? 5.9 centimeters, or let's say kilometers or feet, what? And 62 what? 62 kgs, 62 kgs or 62 pounds, right? So this unit is very important. Similarly, when we measure the asymptotic complexity of an algorithm, we may say that this complexity of a function is is 5n plus 3, but after ignoring this plus 3 and 5 we are left with n. But again we need to have a unit with this n as well, right? And for that, it's the unit is not kilometers or centimeters or pounds or whatever. It's not like that. It has different units. So there are multiple units, but the commonly used units are these three. The first one is big O, which shows the upper bound, which shows the worst case of an algorithm. The other unit is called omega, which shows the best case of an algorithm, and the third unit is the theta, which shows the tighter bound, right? Now before going into the specifics of these three, I need to explain what is the best, worst and tight or average case of an algorithm. For example, this is an array, okay, and in this particular array there are certain numbers, right? We have got 7, we have got 8, 11, 6, 2, 1, 0, and we need to search a number. Now in the worst case, the number which we are searching will be in which slot of this array? Think about it for a while. No, it won't be in the last slot. In the worst case, it won't be in any slot, right? And maybe in the last slot as well. So in the worst case, you will be checking index number 0, then index number 1, then index number 2, and index number 3, index number 4, 5 and 6, and you come up to the 6th slot and you do not find number, then you simply display the message, okay, the number is not found. So this is the worst case. So the worst case is always represented by big O. It is written as O, big O. There is small o as well, but we are talking about big O, and small o is basically, we have a different course on the analysis of algorithms, and there are multiple techniques, but a primary focus of this course is on data structures. Although analysis of algorithms is important to have a variation between different data structures, so that much knowledge is being expected here in data structure. The detailed analysis of algorithm course will be, I think it's in your 7th semester or 8th semester. Anyways, coming back to what I was saying is that the worst case analysis, worst case time of an algorithm is represented by big O. Now if we write a piece of code for this algorithm, so we will be running a for loop from I is equal to 0 to up till n, right? So in this particular case, the worst case time complexity will be order of n, right? Then now let's come to the lower bound, which shows the best case. In the best case, the item which we are trying to find is in the first slot, right? So as we reach the first slot, the item is there. So in that case, the complexity will be omega of 1, and in the tighter case, the item will be in the middle of the array, right? But we are always interested in the worst case or the upper bound of an algorithm, because when we know the upper bound or the case where the algorithm performs the worst, and we try to fix our code so that it works better in the worst case, automatically the average and the best case have good chances to perform better. Now this big O is the term which is the unit rather which we will be using throughout this course. Now the definition of big O. Okay, the graph is here. Okay, now let's suppose if we have a function f of n, this is a function, this can be like 5n plus 6, and we have another function which may be like 3n square. So these are two functions. We are not discussing what actually the value of function is, but these will be the two functions. Now if f of n and g of n are two complexity functions, we say that f of n is big O g of n, right? It is also read as f of n is order g of n, or f of n is big O of g of n, right? So this big O is also called order, right? And I will be most probably I will be using the word order in the remaining of the course, right? Now f of n and g of n are two complexity function. F of n is equal to big O order of g of n if there are constants c and n naught such that for n greater than n naught, f of n is greater than or equal to g of n. Okay, now and I am sure that you could not understand this, right? So let me draw it here. Now this will be the time, this will be time, this will be the size of the input, right? And let me draw a line, and okay, let me draw it blue. This line, if you see here, this is the line, and let me call this line f of n, right? This, and I'm not mentioning any function here, but I'm saying that this is this line represents f of n, right? And then we have another line, okay, this line, and this green line represents g of n. Okay, now this s represents size of the input, time represents, t represents the time. Now this particular point, if you see this point, this and these will be numbers 1, 2, 3. Okay, let me write 0, 2, 4, 6, and so on and so forth. Now at this particular point, we call this particular point, which is again which represents the value 6, right? This point we call n naught. Now let us read this line. Now if f of n and g of n are two functions, f of n is a function, g of n is a function, and we say f of n is order g of n if there are constants c, and I have not written c here, we can use that, but I am ignoring that, and n naught such that for n which is greater than n naught. Now if you see value of n, size of the input is 0, 2, 4, 6, but after this 6 n gets, let's say 7, okay, let me write it as 7, 8, 9, so on and so forth. Now after this particular point, this f of n is always greater than what? It is greater than g of n. So after this particular point, before this, or okay, before this this n naught, g of n is greater, right, in terms of time, but after this n naught, the value of f of n is always greater than or maybe equal to, but it's the way I have drawn this line, it is not getting equal to. After this particular point, f of n is always greater than g of n. So it means that this f of n is big O, big O of the, ये तो मैंने बहुत गड़बड़ कर दी, big O of the g of n, right? So we can call it that f of n is the asymptote of g of n. Or iski, if you see this example, the example of of a particular of a hypothetical student and then a topper of the class. So this f of n is the topper of the class, this g of n is a different student in the class. So this value of g of n is always less than this f of n. So f of n is the asymptote of g of n, right? Right. Okay. So so now given given that definition of the big O or asymptote, now let us come here. If we see here, this apparently 10n square versus n cube is an example, and n cube is apparently more than 10 into n square. And if we see here, this pink line represents 10 into n square. Initially this pink line has more values, but after this particular point the behavior of this yellow line is has increased abruptly as compared to the pink line. So after this particular point, this yellow line has become asymptote or big O of this pink line. It means that n cube is asymptote of n square, right? So this is how this asymptote or tighter bound, or rather bound, not tighter bound, I will be explaining what is tighter bound later, is expressed, right? Now the same thing is explained. I drew the figure while I was explaining the concept of asymptote here. So the same sort of figure is drawn here. And if you recall, in the initial, in the first lecture, sorry, I told you that there is a book of Introduction to Algorithms by Corman. So this graph is there. If you guys have purchased it, it will be very useful. But if you don't feel like spending money, you can drop me an email. Maybe I've got it in the soft copy and I'll be sharing it with you, and we can upload it on the CMS as well. Now if you see that 7n minus 3, now if you see, for example, if a function, if we compute a function for a given code and it says okay 7n minus 3, and we say that okay this 7n minus 3 is order of n cube. Now what does it mean? It means that if the n cube is like this, n cube is like this, and this 7 okay, let me recall, this 7n minus 3 is like this, okay. So this blue line will always remain less than this red line, but it is better to say that this 7n minus 3 is order of what? Order of n, because we need to give a tighter bound. We don't need to give a very higher bound. Now to give you an example, previously in the last lecture I gave you an example of the mobile phone, but for example if a student comes into the class with a very beautiful watch in his or maybe her hand, and okay, I'm trying to make the watch, okay, let me redraw it, wait a second. This is the watch. It's more like a ring maybe, but it's a watch. Let me write here, watch, right? Now, and for example this student has this watch with him, and this student likes the watch, and he says okay, I would like to purchase the same watch. From where did you get it? The student says okay, I got it from, let's say I got it from Rawalpindi, for example. Okay, he says okay, from which shop? He tells him the shop, for example. he says okay, I will go there on the weekend and I will purchase it. And what is the price of the shop, price of this watch? And this guy says okay, this watch costs Rs 600,000. So if you go there, you need to have 600,000 rupees with you. 600,000 means 6 lakh, right? But probably this watch may cost around, let's say, 10,000, right? So there is a huge difference between this 600,000 and 10,000. So telling this poor man that okay, when you go to purchase this watch, you should have at least 6 lakh rupees with you is way too higher amount. Okay, you can say okay, this watch is around 10,000, but these days everything is getting expensive, so you better should take with you 15,000 rupees. Maybe you would like to have a cup of coffee later, or give a treat to your friends and stuff. So this 15,000 is a tighter bound, which is better, instead of giving a bound of 600,000, 6 lakh, right? So same goes for this asymptotic analysis. For this 7n-3, we may say that it's order of n cube, but that is far higher bound. So the tighter bound or the tighter approximation will be order of n, right? So we always need to have the tighter evaluation or the tighter bound when we report the asymptotic analysis of a piece of code. So that is sufficient. In the next lecture, we will be having some example codes, and we will be computing their time complexity in terms of big O.